Okay, hello and welcome to a new video. In the last video we maximized the Shannon entropy using calculus of variations, and we found that under certain boundary conditions, under certain constraints rather, that yields the normal distribution. And in this video we are going to be doing much the same thing, however with slightly different constraints, which will hopefully yield the Maxwell-Bolzman distribution. I think this is a really cool quirk of, well, I mean, it makes a lot of sense if you think of it more theoretically than mathematically, but I think this is the beauty of the Shannon entropy to some extent. So anyway, we will begin. I've written up the Shannon entropy regarding the probability density P of a particle's velocity vector V. I should really give, I'll just do V arrow, and those are scalars. To be clear of the notation, V sub x is just the x component of V. I can actually say here that V equals to Vx, Vy, Vz. This is just horizontal vector format. Let's first begin by writing out our constraints. Similarly to last time, we have our first constraint, which is so. Sorry, d cubed v is minus 1 is equal to 0. And our second constraint, now E here is regarding the kinetic energy, the average of which is fixed. So, over our r cubed space, this is just standard three-dimensional space, v squared p v d cubed v, obviously because it's over the three dimensions, and this is just standard, I come to understand this is standard notation in statistical mechanics, meaning the average kinetic energy. And of course here v squared is just the absolute of the squares of the velocity components. Yeah, the sum of the squares of the velocity components. There we go. And we can use these two boundary conditions to construct a Lagrangian functional. So our Lagrangian of P, and we'll have Lagrange multiplies alpha and beta here, so over r cubed again, minus P v ln P. This is just our original original Shannon entropy, minus, and then our first boundary condition, alpha P v minus beta half m v squared P v d cubed v plus c. And the condition for the extrema is that, oh gosh, my deltas are not on point. That'll do. The derivative of the Lagrangian with respect to the probability density, not rho, p, is 0. And so we can differentiate the integrand with respect to p. So the partial here with respect to p of the first part, which is minus p ln p, is just minus ln p minus 1, because it's p over, it's just actually p times 1 over p, which is just minus ln p minus 1. And the second part, with respect to p of minus alpha p, is just minus alpha. And the third part, yeah, I do them like that. Okay, good. That one was particularly ugly. That's why. Okay. Of minus beta half mv squared p is just minus beta half mv squared. And now, of course, we set the sum of these terms to be 0. So minus ln of pv minus 1 minus alpha minus beta. I'm going to pop these because they're all constants. So m over 2v squared is equal to 0. And what we aim to do here is solve for PV, or rather, we arrange for ln PV and then exponentiate. So that's ln PV is minus, I'm going to take the minus out of both of those, so that's 1 plus alpha minus beta m over 2v squared. And we exponentiate both sides, so PV is it definitely is exponential of minus 1 plus alpha exp of minus beta m over 2 v squared. Cool. Now we're going to define normalization constant, which is a I'm not gonna actually, yeah, I'm gonna define a as this e to the minus 1 plus alpha cool. Yeah, normalization constant, partition, same thing, kind of. Anyway, we can substitute in the parts of v squared here, so we can say that p of v, remember earlier, right at the beginning, I said that v squared is vx squared plus vy squared plus vz squared, so pv is a times the exponent of minus beta m over 2 vx squared plus vy squared plus vz squared. And this factors into 3 independent components. So we can say that's a, I'm going to use dot to mean times here just because all of this are scalars. E to the minus beta m over 2 v squared times e to the minus beta m over 2, oh, this should be vx squared, and then that's vy squared times e to the minus beta m over 2 vz squared. Yep. And now, of course, we enter the long process of solving for all the constants. So remembering our first boundary condition, which was for this to be equal to, or rather for that to be equal to 1, what we're going to do is integrate this over r cubed. So r3 of that, which I'm going to copy and paste because I'm not going to write all of that out again. Hey, nice. And this has bounds of integration dvx, dvy, dvz equals 1. I can actually just say d cubed v here because it's still r cubed. D cubed v is 1. Obviously that refers to those separate bounds. And now integrating each one of, well, first of all, a is a constant and it's not dependent on v, so we can take that out. So our final answer is going to have A at the beginning. Now, the Gaussian identity from the Gaussian integral says that for the integral from minus infinity to infinity of e to the minus k x squared dx is equal to root pi over k. And our k here is minus beta m over 2. So all of these are going to be, you're going to have the product of 2 pi over beta m, so that's cubed, that equals to 1, therefore a is beta m over 2 pi to the 3 over 2. I'll reuse that because it's a bit of an easy way to write it. So now we have a, which is great. We still need to find beta though. So we can use, I'm not going to derive the kinetic energy temperature relation. If you'd like to do that, then I will link a good derivation of it from a textbook in the description. I'll have to remember to do that. I'm going to write myself a note in a new tab so that I don't forget. Link textbook. Cool. I'll do that, but we know that average kinetic energy is 3 over 2 kBt, where this is the Boltzmann constant, and so we know that this is what our constraint is equal to, the energy constraint. And so I'm going to say half and m here are constants. That's not a very good integral. I'm going to put this one over r cubed as well, just for the sake of not writing much. D cubed v is 3 over 2 kBt. Brilliant. And we assume symmetry here, and the assumption behind that is that if you have got enough particles in a box, there's going to be an average number going in all directions to an equal extent. And so we can assume that Vx and Vy and Vz, or rather the average, assuming, because we're lazy physicists, Vx squared is equal to Vy squared is equal to Vz squared. Averages, of course. So it's just, so we can shorten that integral down to half m3. Oh, actually, I can write 3 over 2. Oh, look. 3 over 2m integral over r cubed of v squared x pv d cubed v is 3 over 2 kbt. Get rid of that. And okay, yeah, he says. I'm also going to sub in just our x form of p of v, so that everything's in terms of v sub x. So m times the integral from minus infinity to infinity of vx squared times this. That was the world's worst beta. E to the minus beta m over 2vx squared dvx kbt. Right, I'm happy with that. Now we're going to sub in a variable lambda and do some trickery to find out what beta is. So, we'll let okay. Say I of lambda is equal to the integral from minus infinity to infinity of e to the minus lambda u squared du, which is of course just root pi lambda to the minus half, because that's the same as writing root pi over lambda. And we're also going to say that lambda is beta m over 2. Now we can find the integral of, well, first of all, we'll take the derivative with respect to lambda of both sides. Half. Yep. And this is the same as minus u squared e to the minus lambda u squared du, and that's just minus a half root pi lambda minus 3 over 2. And now we have an expression for this, which shows itself in that integral there. And we can even shorten this down to be 1 over 2 lambda root pi over lambda. And so clearly here, well actually let's sub that in. So m root lambda over pi times that integral from minus infinity to infinity of v squared e to the minus lambda v squared x dvx, I forgot x there, equals 2kbt. And then that just gets substituted into that thing. And of course the root lambda over pi and root pi over lambda, those two are going to cancel out. So m over 2 lambda is equal to kbt. And so 2's would cancel out when you plug in lambda, so it's m over beta m is equal to kbt. 1 over beta, I forgot that m's cancel out as well, is equal to kbt, and so beta is equal to 1 over kbt. So now using our trickery, we have values for alpha and beta, which we plugged in with our maxim from earlier. See, this is a lot easier now that I've already done it once for the last one. And also, I think with the Maxwell-Bolzman distribution, there's just a bit less to do. There's only 2 constraints, so there's only 2 variables, so it's kind of easier. Anyway, subbing that back in, we get that our normalization constant is, I keep forgetting my equals today, m over 2 pi kbt. I'm the king of algebra. 3 over 2. So P of V is m over 2 pi kbt, 3 over 2 times the exponent of minus mv squared over 2 kbt. Yep, I'm happy. And now the last thing that is done is kind of a pain. Calculus 3 stuff, we need to switch from Cartesian to spherical coordinates. and that's so that we take angles into account. So what we're going to do is define a new function f of v, which is obtained by, just as a reminder, the spherical coordinates here. We go from x, y, z to v, theta, phi. Greeks really love putting lines through the middle of their letters. They do it quite often. Silly observation of the day. Anyway, and here d cubed v becomes v squared sine theta dv d theta d phi. I know this, I can't remember where it comes from, but you can find it in a Calc 3 textbook somewhere. F of v dv is, so now we're integrating over angles theta and phi to account for them. So that's between pi p of v squared sine theta d theta d phi dv. Yeah, I'm okay with that order. Which is, you can pull that out, p I realise I should say that v is just the magnitude of that v. So pv v squared, integral from 0 to 2 pi d phi, and then just the integral from 0 to pi of sine theta d theta. I wonder what that could be. So this is just 2 pi, and that's just minus 1 minus 1. No, minus 1 minus 1. Minus 1 minus 1, just 2. So the factor that we get from that is f of v equals p v times 4 pi v squared. So that's our spherical surface area factor, because we're treating all particles as spheres. Because, you know, that's the truth, and anyone who disagrees, like people who say that lead-208 is an oblate spheroid, they're just telling lies, because they want to be special, they want to be different. But everyone knows that the lead-208 nucleus is a perfect sphere, like perfect. I am being extremely sarcastic. I'm not sure if it's coming across, but please don't believe that. It's a lie. It was a deliberate funny. Anyway, subbing that back in gives that f of no vector is that times 4 pi v squared. So we can put it in its final form, 4 pi v squared over 2 pi kbt. That should be a b, not a beta. Oh, I've already messed that one up, haven't I? bt exponent of minus mv squared over 2kbt. There. And we can safely, oh, well, if I could draw one, we can safely pop a box around that, as that is the general form of the Maxwell-Bolzman distribution. And as you can see, that has been derived via calculus of variations completely from the Shannon entropy for a 3D particle. So yeah, just kind of a follow-up to the last video. I thought it would be nice to present the symmetries of what you can do with the Shannon entropy. There's a lot more to it. It's amazing. But at the very least, these are two things that I can do with it, and they're pretty cool. So yeah, I hope that you enjoyed this video, and I will see you next week for another one. Goodbye.